Hi learners, have a very good day. So till now we have become familiar with all the basic concepts of the control system. We have come to know what is time response, what is frequency response. For reference, you can check my previous lectures. Today I am going to discuss a very important technique that is used with the control system, that is the root locus technique. So what is root locus? Root locus is because what we have understood till now, that location of the roots of the characteristic equation play a very important role in determining the stability of a system. In case all roots of the characteristic equation are lying in the left half of the S plane, then the system is said to be stable. And root locus is what? This is a technique which provides a graphical method of plotting the locus of the root as system gains varies from minus infinity to plus infinity. When the system gain is varied, corresponding to that, the location of the roots of the characteristic equation will also be changed. So when gain varies from minus infinity to plus infinity, then we try to draw the locus of the roots of the characteristic equation, and that will give us information regarding that for what value of gains the system is stable, for what value of the gain the system is unstable. It will help us to decide about the stability of the system, and also gives a number of other information that we'll be discussing at the last. So roots of the characteristic equation are given by KGSHS, because characteristic equation of a system having a gain K is given as 1 plus K into GSHS equal to 0. So its roots are given by K into GSHS equal to minus 1 plus J0. So we equate the angles of both the sides and magnitude of both the sides. We'll get magnitude of GSHS is equal to 1 by K. This is called magnitude criteria. And angle of GSHS is equal to plus minus 2Q plus 1, 180 degree. So this is called angle criteria. Q varies from 0 to 1, 2, and so on. So this is the angle criteria. So at each and every point of the root locus, both magnitude and angle criteria are satisfied, because root locus is what? Locus of the roots. So on the locus of the roots, the magnitude and phase criteria will be satisfied, because the roots of the characteristic equations are uh, uh, are are specified by the equation KGSHS is equal to minus 1. Then what are the rules for the construction of the root locus? First rule is that root locus is always symmetrical about the real axis. Second rule is that if we have an open loop transfer function of the system that is represented as equal to GSHS, P is equal to the number of open loop poles, Z is equal to the number of open loop zeros. Then the total number of branches of the root locus, that will be equal to P. Out of these P branches, Z branches will be terminating at the open loop zeros, and P minus Z branches will be uh, terminating at infinity. So total number of branches of the root locus is equal to number of the open loop poles of the transfer function, open loop transfer function of the system. Out of those, Z branches will be terminating at the open loop zeros, and rest of the branches will be terminating at infinity. Rule number 3 is what? A point on real axis lies on the root locus if the sum of the number of open loop poles and open loop zeros on the real axis to the right hand side of this point is O. To determine whether certain portion of the real axis is on root locus. What we'll say? We'll just calculate the total number of open loop poles and zeros to the right of that particular point. In case the total number of poles and zeros come out to be odd, then that portion of the real axis will lie on the root locus. Rule number 4. We have said that there will be p branches of the root locus. These branches will be out of these branches, few branches will be terminating at 0 and the rest of the branches will be terminating at infinity. Then along which direction these branches shall be terminating, or these branches shall be progressing? They will be progressing along the angle of asymptotes, which are given by theta is equal to 2q plus 1, 180 degree divided by p minus z. So, so this is equal to where q is what? Q is equal to 1, 2 up to p minus z minus 1. So all the angle of asymptotes are given by this expression. Now, where we'll draw these angle on the real axis? For that, we have to determine the centroid point on the real axis. That is determined by sum of real part of poles of GSHS minus sum of real parts of zeros of GSHS divided by total number of poles minus total number of zeros. So that is the common point termed as centroid. Then rule number 6, the breakaway point. Breakaway point is a point on the root locus where multiple roots of the characteristic equation occur. Means there are a number of branches of the root locus. They are coming towards each other, and where they'll just depart or they'll move away from each other. So for that, we just calculate the breakaway point, and these branches, the root locus branches, leave at breakaway point at an angle of 180 degree divided by n. So if there are 3 branches which are meeting at the breakaway point, then they'll be departing, they'll be leaving it at an angle of 180 degree divided by 3. Now, how do we determine the breakaway point? Because when the branches are coming, where they'll break away, that will be decided by just taking the roots of the equation dk by ds is equal to 0, for which k is greater than 0, it gives the breakaway point. Then next, the intersection of the root locus with the imaginary axis is determined by using the Routh-Hurwitz criteria. Then in case we are left with the complex poles from which the branch of the root locus is just emerging. So the angle at which the branch departs from complex pole, it is called the angle of departure, and it is represented by 180 degree minus phi. What is 180? Phi? Phi is equal to the contribution of the angle made by remaining poles at the poles at which phi d is to be calculated, and sigma phi z is what? Contribution of the angles made by the remaining zeros at the poles at which phi d is to be calculated. This because the branches will be leaving the poles, so the phi d is representing the angle of departure, and the branches will be arriving at the complex zeros. So it is there, that angle is represented by phi a. Phi a is equal to 180 degree phi, and phi is calculated in the same way as we have calculated earlier. Now let us take up an example and we try to get the draw the root locus plot for the same. So GSHS, here we are taking a system for which the open loop transfer function, this is a feedback type of the system for which the GS is representing the transfer function of the forward path, HS is representing the feedback path transfer function, GSHS is representing the open loop transfer function that is given as k divided by s into s plus 5 divided into s plus 10. So first step in drawing of the root locus will be to draw the pole 0 plot. So in this case, we cannot find any 0. We are having 3 poles at s equal to, poles are obtained by equating denominator as equal to 0. So poles lie at s equal to 0, s equal to minus 5 and s equal to minus 10. So these poles are represented by a cross pole at 0, pole at -5, and pole at -10. Then we have to determine that which portion of the real axis is lying on the root locus. So if we see to the right of the portion of the real axis to the right of -10, we can very well see the total number of poles and zeros to the right of this is 2. So it means that from -10 to -5, the real axis is not lying on the root locus. Then from -5 to 0, if we look at the right to it, we can see that there is only one pole. Odd number of pole is lying. So it means that the portion of the real axis between -5 and 0 is on the root locus. Then portion to the left of -10, if we look at the right side of it, we can find 3 poles. So it means that to the left of -10, whatever portion is lying, that portion of the real axis lie on the root locus. Then we have to determine the angle of asymptotes. Angle of asymptote is given by 180 degree into 2q plus 1 divided by number of poles minus number of zeros. Total number of pole is 3, number of zero is 0. So this will be equal to 180 degree divided by 3, 180 degree into 2q plus 1. Q is 0. First of all, q is 1. Then it will be 3 into 180 degree divided by 3. Then it will be 5 into 180 degree divided by 3. So the angle of asymptotes are 60 degree, 180 degree, and 300 degree. So at what point we should draw these angles of asymptote? For that, we have to determine centroid. Centroid is sum of real part of poles minus sum of real part of zeros divided by total number of poles minus total number of zeros. So sum of real part of the pole is 0, -5, -10, and of 0 there is no 0, divided by number of poles is 3, number of 0 is 0. So it will be -5, -10, -0 divided by 3. So it is coming out to be -5. So we can very well see that -5 is the centroid at which the angle of asymptotes are to be drawn. So this is -5. This is the centroid at which we have drawn three asymptotes, one at an angle of 60 degree, another at an angle of 180 degree, and the third one at an angle of 300 degree. Now, since we are having 3 poles, so it means that there will be 3 branches of the root locus. And what will be the breakaway point? That is to be decided. So that is decided by just taking dk by ds equal to 0. It gives -2.113 as the breakaway point. Then the intersection with the imaginary axis, it can be simply calculated by considering s cube plus 15s square plus 50s plus k equal to 0, because this equation we have just derived from here. This is s cube plus 1 plus gshs is equal to 0. We have just taken this equation, and the solution of this equation by using the Root array, we have determined the value of k for this that we should follow, and corresponding to this value of k, we have determined the value of this one s. So you can very well see we had one pole at here, one pole at here, one pole at here. Then we had determined the centroid as equal to -5 and breakaway point as equal to -2.113. So we can very well see that this is equal to centroid, -5 at centroid. We have drawn the asymptotes. Then this portion of the real axis is lying on the root locus, because to the right of it, the total number of pole is 1. This portion is not on the real axis, because to the right of it, total number of poles and zeros is equal to 2. And this portion of the real axis is also on the root locus. Then there are 3 branches of the root locus starting, because there are 3 poles. So 3 branches of the root locus are starting. Each branch will be terminating at a infinity, because there is no 0. In case there had been any 0, then the branches, few branches would have terminated at zeros. The rest of the branches would terminate at infinity. But in this case, we can very well see that no branches is terminating at none of the branches terminating at infinite at 0. So all the branches will be terminating at infinity. So one branch will start from here, it will go in this direction, and it will be terminating at infinity. Another will start in this and it will go in this direction. The next one will go in this direction. Uh, then we have just determined the breakaway point. This breakaway point, they will break away at an angle of 180 degree divided by 2, that is 90 degree. They will break away like this. Then they will be moving in the direction of the asymptotes like this. Then we have calculated this point. This is the breakaway point by taking the taking the derivative of k with respect to s and substituting it as equal to 0. So this breakaway point is calculated by just taking dk by ds equal to 0. Then we have calculated the intersection of the root locus with the real axis by using the Routh criteria, and intersection is obtained at j 7.07 and at minus j 7.07 that we have just calculated over here. This is j 7.07 and j minus 7.07. Here we have got the intersection with the imaginary axis. So with this, we have completed the root locus plot of this simple open loop transfer function by following the step that we have discussed within this lecture. I think this lecture will be beneficial for you to draw the root locus and it will be helpful to you to learn the steps to draw the root locus. Next, what information we can get from the root locus? First is the gain margin. This is the value of k at the stability boundary divided by the design value of k. Gain margin is basically defining the relative stability, and this is equal to the margin by which the system gain can be increased so as to drive it to the verge of instability. So that is the gain margin. So value of k at the stability boundaries. What is the stability boundary? Stability boundary is the imaginary axis. So value of k here or the value of k here divided by actual value of k that we are using within the system. It might be given. So this is equal to this. So k is not given over here. So in case k is given to us in any particular example, then we can get the gain margin. Then like we have derived the value of k as equal to 750 over here. So we are using k. This is the value of k that is determined from the this one. This is the intersection with the imaginary axis, and that is determined with the help of the Routh array, and gain margin can be calculated by using this relationship. Value of k at the stability boundary, that is on the imaginary axis, divided by the design value of k. Then in order to determine the gain factor at the point of intersection with root locus, that is the required value of k. So what will we do? What will be the gain that will be achieving with at a particular damping? To calculate that, we'll just draw a line that is like damping is specified to be zeta. Then we'll just draw the angle theta as equal to cos inverse zeta. Then we'll draw a line that is making an angle of theta with the negative real axis, and wherever it intersects the wherever it intersects the root locus, at that point we will get the value of k, and that will be the gain fact. That will be basically the value of the gain at that particular value of the damping which is specified. So root locus directly gives us an information regarding the locus of the root. It is giving you the graphical representation at the system gain is varied, and it helps us to find that what should be the value of k and which value of k should not be crossed. So it helps us to determine the gain margin as we have just shown by this relationship. At the same time, it helps us to determine the value of the gain for a specific damping ratio zeta. So zeta is specified. We'll just calculate theta is equal to cos inverse zeta. We are having a root locus plot. Then we'll just take up the intersection of this line that is making an angle theta with the negative real axis. Then with the root locus, then at the point of intersection we'll get the gain that will be the required value of the gain that is asked. So within this video I've tried to make you aware of the all the steps which are being used for the construction of the root locus in a very simple way. I hope that you'll get benefited from this lecture, and you'll draw a number of root loci plot, and you'll try to get gain margin, then the gain factor at the point of intersection, and a few other information from the root locus plots that you will make yourself. Thank you so much for the patience learning and patience hearing. So I just stop over here. Thank you so much.